We better not to answer this question.
No, quelqu'un qui est expert, quelqu'un qui va la base sur ça, il faut quelqu'un qui
He's not here.
Is there a reason?
Non, mais pour la présentation, c'est pas une on travaille sur on travaille dans la présentation. Non, c'est pas ça.
No, we are on record. Yeah, it's close. That's why I'm going to do it.
Tu n'as pas encore le problème. Le problème exactement que tu vas traiter.
No, I only read the first part of both of them.
Non,
No, I read the first part of both of them. Then I stopped.
c'est pas une
I thought that was
exactement.
You are going home and
Mais pour comprendre le problème.
someone wants to buy
J'ai compris ça.
You got the set of equations and
This one? No, I don't have an ocean back. Last month I saw the I saw it was not good. Sometimes I did not
I was thinking how to convert this into again in mathematics. I was thinking. But I didn't think
Last time I disconnected.
Okay, so it's better policy.
And I know that this solution is
for pointer matching.
yes.
okay. Three, 4, 5, 8. Where are other people? Not interested. So we first I used to reconnect the PC with the laptop and then put it back. Because of course we can do the solution. So at least once I do it properly with your laptop. It shows this PC.
Okay. At least something is there.
Yeah, I see. Okay. So now one more person, right? Still not 10. But anyway, look, before I start showing that, I would like to make a few comments about your exam. You know, I didn't check it. I didn't check everything. I just made a quick look, and you disappointed me a lot. Look, really, I even had doubts that should I show it to you because of mistakes were so unexpected. I don't want to put name. I don't want. But look, one of the problems for Fermi gas. I'm starting with Fermi gas. This 1 over n e squared minus e over n squared. By the way, it's written correctly what it is because each average gives you integral over dp, and there is a volume inside, and volume inside is concentration. So this is epsilon p squared np minus, and here it's again volume 2 pi cube over n integral over dp 2 pi cube epsilon p np squared. You see that the dimension of each term is correct. Namely, this should be some coefficient times Fermi energy square minus another coefficient times Fermi energy square. So what one needs to do is actually to do simple arithmetic calculation, namely 37 minus 9 divided by 25. How come that only one person did this simple exercise correctly? How happened that I saw in one word that 37, minus 9 over 25 is equal to 163, 125. How can it happen? This number, this fraction, is clearly less than 1/2. This fraction is clearly bigger than 1/3. If one subtracts something which is bigger than 1/3 from something which is smaller than 1/2, how one can get something which is bigger than 1/2? It's a simple arithmetic. So really, I understand that you are under stress in exam, but look, either you are very inaccurate, and this is, I very much hope, is the case, or you don't know how to do arithmetics. And if you don't know how to do arithmetics, what is the further reason to discuss nanostructures or whatever? I probably need to do with you exercises about arithmetics. Well, this is, you know, I deliberately constructed problem such a way that it tests different skills of you, both mathematical and physical. By the way, most of you didn't recognize the proper dimension, putting something like 1 over n in front. But look, when I gave you this examination work, don't you think that I'm also inaccurate or irresponsible to give you something which contains mistakes? Of course, we are all human beings and we all can do some mistakes, but if you see that I did mistake, which also can happen, why don't you come and ask me? And but before asking, please think twice whether it's mistake or it's some misunderstanding. And if it's your misunderstanding, why not to come and ask? So this is simple arithmetical. Second, most of the first problem, well, C dot P, where C is a constant vector, is of course some constant vector times average value of P. So actually there were two exercises associated with the calculation of average value vector. Only few people tell me correctly that they don't want to calculate this quantity just because it is zero by the definition, since you don't have any preferable direction in the system, and due to symmetry reasons. Everything is unimportant. If temperature is equal to 0 is important, No, it's unimportant. It's important that this dimension is equal to 3. No. Is it important that this is ideal Fermi gas? Epsilon P is P squared over 2m? No, it's not important. So just due to symmetry reasons, it has to be 0. Most of you obtain that average value of vector is first of all equal to scalar, which is not equal to 0. The question, how come? How can you get this result? And can you, with thinking, can you understand the consequences of this? And actually, what are the consequences? You put a piece of metal on a table, and this piece of metal moves in some preferable direction. This is the physical meaning of this result, if you manage to get it. Can you imagine it physically? How a piece of metal can possess non-zero momentum. Non-zero momentum means it is characterized by non-zero velocity. And non-zero velocity means that piece of metal moves on your table. I believe you should have made this exercise in statistical physics or whatever, and this is very simple exercise which doesn't require any calculation. It's just thinking and understanding what you are doing. Really. And I will not close my eyes for this kind of mistake. Those who did that don't expect any excuses. It's not lack of mathematical skills or elementary school mathematical skills. It's lack of understanding of anything happening, which is very sad for me. I probably was a bad teacher. I didn't teach you properly about things. Clearly I did my best, but look, it's really a shaming things. Another thing, these were two trivial examples showing the lack of skills in arithmetics and lack of understanding of simple things. But there was some a bit more complicated thing. There was a Langevin function x, which is cotangent x minus 1 by x. And what I actually asked you to differentiate this Langevin function dl x with respect to d1 over x. Literally speaking, it was the case. And then to plot the sketch plot of this curve. It appears that most of you don't know how to differentiate function properly. And those who manage eventually to differentiate it properly don't know how to plot the picture. How can it happen? This is elementary function. So this function is elementary and this function is elementary. Can you plot elementary function? You must. I can understand that sometimes calculating of integral can be tricky, because calculating of integral is art. But taking its derivative is just a stupid machinery. You do it 1, 2, 3, and you got the result. You don't, if you forgot something, you just come to the definition, whatever definition you like. If you like that cotangent x is equal to cos x divided by sinh x, you go with this. If you forgot this definition, go with exponent e to the power x plus e to the power minus x, e to the power x minus e to the power minus x, and differentiate. The simplest, the only thing you need to know is that the derivative of exponent is exponent. I don't see any point of difficulty in this problem. So you see, I expected that all of you do this, all of you do that. With this, most of you do it correctly. But my expectations were too much exaggerated, and I don't understand the reason of these wrong expectations. So maybe I should give you 10 homeworks, but I rely on the fact that you are responsible physicists. You are not first-year students. You are those who undertake courses of special courses, which assumes that you know something and you are motivated to do something. But how can it be this, and that? I told you many times, if you need a homework, you invent the homework yourself. Just think about problems you can invent, try to solve them. If you don't know how to invent problems, take a good book, Landau book or whatever, where there are problems after every paragraph, after every chapter. And this is the same in any textbook. Just try to solve this problem. If you don't know how to solve this problem, come to me. But you cannot finish the course with answers like that. It's really unforgivable. Well, of course, the problem about magnetic field, namely h squared minus h squared, was one-to-one related to what we did in homework. It was just the same problem written in a bit different language, and I'm happy that most of you recognize and solve this problem correctly. But how can it happen that none of you know how to calculate Fourier transform of two-dimensional Coulomb? Of course, you can forget what it is, although I think those of you who would like to work in theoretical physics should demonstrate some interest and know what the Fourier transform of Coulomb interaction is. If you don't know, you don't need to remember anything. You can calculate all what you need. So what you need to know is E squared over R is a Coulomb interaction, where R is x squared plus y squared plus z squared. So if you have two-dimensional situation, the Coulomb interaction is the same. So it's just rho squared plus z squared, and you take z, the thickness, close to 0. So if you remember the correspondence between three-dimensional Coulomb interaction and its Fourier transform of E squared over k squared, what does it mean to take z equal to 0? You need to take this 4p squared over k squared and integrate over k perpendicular from minus infinity to infinity. Why? Because integrating over k perpendicular, and let me put exponent, ik perpendicular z, means taking z equal to 0. So you immediately arrive to this. So if you do that, k squared is of course k parallel square plus k perpendicular square, 4p square over k parallel square plus k perpendicular square, dk. Perpendicular from minus infinity to infinity. So what do you get is 4p square over k parallel, and here it is arctangent k perpendicular of k parallel from minus infinity to infinity. What is missing is of course 2 pi, which so it's 2 pi, pi cancelled, factor 2 cancelled. So in total, arctangent in this two limit is equal to pi. It's 4 pi squared over k parallel to the first power. This is a Fourier transform of two-dimensional Coulomb. And this we discussed many times. Of course, you can take definition and try to do it directly. And the difficulty is then you need to know what the Bessel function is. Or look into the textbook and see. Only one person said it correctly, that it will be some constant divided by k parallel, and up to some constant, which in principle I didn't require to calculate. It's like this. It's like that. It's k to the first power being contrasted to k to the second power for three-dimensional case. And this is a good answer. At least the person demonstrated his way or the way to think. But you see, it's a simple exercise with a simple integral, with a simple elementary function there, which in principle gives you proper coefficient and proper behavior, which then one needs to plug into Bogoliubov formula, which is k squared over m times this Coulomb interaction 2 pi e squared over k times density plus k squared over 2m squared. Therefore, one gets square root of k, where k is parallel. Parallel, parallel, parallel. Square root of k parallel spectrum. So this is epsilon k for two-dimensional. So you see that all calculations took few lines. The formula for spectrum was given to you. You're supposed to know it. So what you need is to figure out correctly what the Fourier transform of Coulomb interaction is and plug it into known formula. Of course, for this problem, I didn't have big expectation that everybody solved it. Although, tell me, what's the difficulty? What is complicated in this logic? If there is some complicated integral, no. But I'm sorry, I don't need to give you hint for everything step by step. You should demonstrate your ability to think. But I'm very much upset that most of you did not. So as you said, you made me very upset. Really. Okay. So let's come to discussion, although I don't look. Offering you this bonus meant that you do your best on exam. I believe you tried, but I would really like to understand the reason behind of such kind of incorrect results. You know, if one is nervous, one is under stress, it's impossible that everything is incorrect. One can do one mistake, second mistake, but it's really a lack of understanding of most of the basic things discussed 1,000 times during the course. Okay. So, of course, I will look very carefully through each and every work. But my first impression is very bad, so don't expect that the outcome of exam will be great. And actually, I would also like to say, if there are mistakes of that sort present in your work, don't believe that there will be any room for negotiation. I can forgive arithmetic mistake, but not of what we want. Okay. Any comments? Any answers? Any explanations why it has happened? The most frustrating point that this is massive. This is not one person who misunderstood. This I discussed mistakes which were very common for most of the works. Okay. Good. So I wanted to show you something about quantum dots, since thanks for planning to teach probably one of next year something basic of transport through nanostructures. So what I'm going to present today for you is basic dictionary of quantum dots and some application of these devices. So this is popular reading. Since you are supposed to get this lecture. By the way, did you get printouts which I gave to Patricia regarding thermals, bosons? I will also give her that, so you will receive it as printed version. And as I said, on a DVD, I will put everything electronically as PDF file, so you will be able to take it home as PDF file. So there is some popular reading, and in this lecture, I'm going to discuss these items, and of course, most of them will rely on knowledge of basics of many body physics, which now I have doubts is the case. Okay, why nano? Why it's so popular to speak about nano? You see, nano is the scale, and typically this size is bigger than the size of molecule, but the size where few molecules form a cluster, because we know that the Bohr radius of hydrogen atom, by the way, how big it is? Tell me. The Bohr radius in centimeters, in meters, in whatever. It's half an angstrom. So the nanometer scale is the scale where few atoms and correlation effect in few atoms of few electron systems start to play important role. So what's subject of this nano? And basically, it's, as I said, many atoms or many electron systems, and I would like to review several examples like quantum dot, molecular transistor, and tell you about application of this science. Of course, it's very difficult to draw the borderline between what is nano and what is meso, because in some cases people are interested in the object which with a typical size few hundred millimeters. This is what I will refer as single electron transistor, and even up to micron. So if system is micron, so micron is 10 to the minus 6, you may estimate how many electrons or how many atoms are there. So just remind you the typical lattice spacing. If you think about crystal, about solid state physics, is about a few angstrom. 3-5 angstrom is the typical lattice constant in most of known methods. By the way, those who are interested, go to Google, go to Wikipedia, whatever, and try to figure out how big the difference is between the smallest atom in the world, hydrogen atom, and the largest atom. So what's the scale between half an angstrom and discover it yourself? And most of you would probably be surprised. If you know answer, tell me. What's the typical size of the biggest atom? If you don't know, it's a challenge to yeah. Okay, today we discuss mostly objects which I will refer zero-dimensional, namely it will be some island of 2 or 3-dimensional electron gas confined in some electric potential, and the day after tomorrow I will discuss physics of quasi-1-dimensional objects, which brings another interesting ingredient into the field. And as I said, the borderline between nano and the meso is very subtle, and for mesoscopic system, of course, the fluctuations associated with fluctuations of potential or disorder become very important. And we discussed some of manifestation of this interest in the scale of mesoscopic physics when we discussed localization, but there are, of course, many more of them. And this is both mesoscopic and nanophysics is one of the most dynamically developing fields of modern condensed methods. One of objectives, you see that this is Intel processor. By the way, the picture is, I think, 2004. And those who are interested in computer technology and read some popular journals or popular articles about this only know about this 90 nanometers technology, or even 35 nanometers technology. I don't follow it closely. This is a way of miniaturization of processors on a computer chip, and in order to come to more and more powerful computers to perform more and more involved calculation, so one of course needs to go to smaller and smaller scales. Of course, not infinity. One cannot go to the scale smaller than the wavelength of electron, which is at the same time is something like 1 strand. So this is ultimate limit, but believe me, many things happen even before that limit. And understanding how far we can go with the semiconductor technology, which is in core on each and every computer, we need to understand a lot of things behind the physics of systems of that size. And those who make logical steps probably realize that for a few last years the processor's stack rate does not increase. It's rather other technologies which are involved, namely power consumption technology, which makes you battery life, longer technology, which makes the voltage of the processor low, which means reduction of heat in the processor, which is very important part, reduction of radio frequency emission through the processor. So there are many ways which limit computer technology. One of them, as I said, the size of your transistor, which cannot be smaller than the wavelengths of electron. Another way is the frequency of the tact rate of your processor, which cannot go beyond this magic gigahertz limit in terahertz range. Otherwise, your processor will be emitting like radium. There is limitations associated with accumulation of heat in the system. Many of them, and this is only stuff related to central processor unit. Of course, building computer. I'm not talking about quantum computing. I'm talking about these devices which are on our desk. One needs to see. One needs to understand physics. For many years, there was something which was called Moore's law. Some of them probably heard about this. And unlike laws of nature, like Newton law, or Einstein law, or Ampere law, or Ohm law, which tell us something about relation between physical quantity, Ohm's law, Moore's law, is a law which invented by IBM engineer, which literally sounds like the processor tact rate is double every 18 months, which was actually the case for almost 40 years. But if we formulate it in a more sophisticated way, it's just reducing the linear size of your technology by a factor of 2 also every year and a half. But this law is, of course, is an engineer law which is just interpolation of the development of science. And of course, what I said before tells you that being not a law of nature, it cannot go to infinity. We have natural limitations, and this natural limitation tell us where to go. And in this lecture, which I offer to you, I try to explain the direction of modern research and new ideas, how one can increase performance of computers from the point of view of hardware. Of course, there is another branch of theoretical physics which is dealing with quantum computation. Namely, instead of having this classical computer which operates with zeros and ones, one may have something which operates with, say, with wave function, with probability density, and then there is a big development in this field, saying what is advantage of quantum computer, namely instead of exponential long computation, we can come at the end of the day to power law, which will then really increase the performance by a huge factor. I'm not going to touch upon the quantum computation things in my talk. I'm just telling you what are the basic elements of the nanotechnology and why it's so interesting and well motivated by experiment to go and see closely what's the physics of nanoscale. And of course, this process, this processor, which involves several billions of transistors, is very complex things, which assumes also the interaction between different parts, and which also assumes deep understanding of controllability of this complex item with respect to applied fields to the system. So, the development of technology, which was achieved in the very end of the 20th century, was based in possibility to fabricate using the lithography method and molecular kinetics such device, which got the name of quantum dots. So what quantum dots are? Sometimes they are referred as quantum dots. Some of these quantum dot devices, the subgroup of them, is referred to single electron transistor. I'll come to that point a bit later. So what was basically is it's a heterostructure of two or more semiconductors. Usually in these semiconductors, like gallium arsenide, lead, aluminum arsenide, are taken such that this is a binary system. One of the elements belong to the third group of periodic table, another one the fifth group. So this is what people call 3-5 semiconductors, and gallium arsenide is one example of this 3-5 semiconductor. But there are other examples and other combinations like 2-6 mercury telluride and cadmium telluride is two examples of 2-6 group. So some of these semiconductors are non-magnetic. Some of them are diluted magnetic semiconductors, which then, in addition to this nanoelectronics, leads to another field which is called for many years as spintronics, as a spin-dependent electronics, which assumes also manipulation not only by electron safe charge, but also spin degrees of freedom in order to provide a building block for hardware, for computer hardware. So, as I said, how it usually looks like. It's two-dimensional electron gas subject to gates, which form a confining potential, and then subject to other external fields like magnetic field, which is one of many controlled parameters. So, being attached to the leads, this island of two-dimensional or three-dimensional electron gas is very well tuned by gate potential temperature field and allows to control the system with an extremely high level of controllability. And of course, if you see that what I started with, namely the size of the system up to 100 nanometers, which is already there in 2004, implemented in input technologies, you see that this is really a few electron system subject to very interesting conditions, namely out of equilibrium conditions associated with the fact that there was a finite current running through the system, subject to external gate potential, which forms the confining potential, and subject to finite magnetic field, and most of the things happen at very low temperatures. So it's quantum system to begin with, and it's a very interesting system. On one hand, contains not so many electrons, but on the other hand, contains enough in order to think about strong correlations in these systems. So what I showed you before, and the first cartoons were related to this so-called large quantum dots of the size of micron, so 10 to the minus 6 meters, but then in 1998, David Gordon from Stanford achieved first fabrication of one of the first fabrication of single electron transistor. And if you can look here, the bar saying that this is 100 nanometers of that. So that's really a linear size of the quantum dot. I don't know if there is a pointer here.
It's a laser.
You see that this is quantum dot. So this is something with 100 nanometers. So the dot is really 100 nanometers, contrasted to this is a dot, and the typical size is micron. So it's really smaller by the factor of 10 of linear size, and therefore smaller by the factor of 100 as far as square is concerned. So this is how it looks like being colored. So this is a quantum dot. The transport goes in this direction, and there are gates applied to the system which provide the confinement potential. Of course, after fabricating the single dot, which was referred as a single electron transistor, because the fact that the transport counts electron by electron, and one can manipulate the transistor containing 5 electrons, 7 electrons, 6 electrons. It's really very few electron system, in contrast to this one, which contains several hundreds of electrons. So after producing the single electron transistor, people start to think about combining quantum dot in kind of coupled devices. So why it is interesting? I will show you later that the single electron transistor or few electron system resembles very much few electron atoms like hydrogen atom. But the advantage is that unlike hydrogen atom, which we cannot catch one and attach leads to them, this is semiconductor technology which allows to study transport through the artificial atom. So the name of artificial atom came to the market, and having several artificial atoms combined with controllable interaction between them, one prepares artificial molecule. So these are building blocks for this semiconductor technology, which are transistors, diodes, and which are supposed to be elements of new process of technology. And you know that what we have in our computers is based on silicon technology. Our Silicon Valley in California, in the States, is something which is a high-tech area, and all our electronics nowadays is silicon-based electronics. Although the first transistor discovered, the Nobel Prize given for this, by the way, Bardeen, who got the Nobel Prize for BCS theory, was the person who got Nobel Prize for transistor. And this was germanium transistor. However, the electronics goes in the way of silicon electronics, and one of the reasons is there was a huge investment in buffers which produce these nanochips using the lithography and so on. So switching to another electronics is very complicated and costly project. So one really needs to convince industry to switch to other types of electronics. And this semiconductor technology based on gallium arsenide semiconductors is something which competes with the silicon-based technology. So this, I said, is double quantum dot, which is kind of artificial molecule. One, of course, for out of two atoms, one can get on a linear molecule, but this molecule, however, can be oriented both parallel to the leads, so these are source and drain, and perpendicular to the leads, so this is source and drain. Again, you see that this is a micron, and this is the size of the dot. So it's really like a point of the pointer. So you see how much it is smaller by the linear size. And of course, people produce more sophisticated devices which can be either linear, so this is triple dot, and this is triple linear dot. You see the development in this field goes in a direction from few electron artificial atom to few electron artificial molecule, because it gives more and more controllability on the system on one hand, but on the other hand allows to do more manipulations with this device. So these were quantum dots obtained by lithography, but of course there are other ways to get quantum dots. For example, this is a called self-assembly quantum dot, which are formed on the interface. These pyramids on get heterostructure, and this self-assembly quantum dot is already kind of nanocrystal. You see that this quantum dot work like atom, and this atom are controllably spaced to other atom, so one can construct artificial crystal. And why do we need to construct artificial crystal? Just because of controllability. We are doing our investigation on the bulk system, whatever it is, normal metal, superconductor, or some material given to us by nature. We are very much limited to what is given to us by nature. Namely, there is no much flexibility to change lattice spacing. Of course, one can apply pressure, but again, look and try to estimate how much one can change lattice spacing if the pressure is applied to system up to very high limits. And we will again be very much surprised. The interactions are given again us by nature, because the interaction is dealing with the structure of particular atoms, structure of particular crystalline lattice. But what is happening here is just we don't expect any gift given to us by nature. We're just coming, and well, not really. People who work in the field coming and fabricating things which possess those properties which we need. In some sense, if we want to study some Hamiltonian, we can come to our friend experimentalist, tell him what kind of Hamiltonian we would like to deal with, and he will fabricate a system which is characterized by this particular Hamiltonian, in contrast to logics of previous century when people were mostly studied invented Hamiltonians in order to describe some particular system, depending how complex it was. Last but not least, one of the very recent development on the field is nanoelectromechanics. And this is a combination of quantum dots and putting some extra ingredient, namely possibility to move this nano-object between source and drain. So you see that these are two electrodes, golden electrode. This is a quantum dot. This is a string. And by applying the microwave, one made this string to move. So therefore, this is non-electromechanical single electron transistor, where the transport through it is also controllable by mechanical manipulation. So this.
What is the string made of?
String is silicon nitride. It's under stress. It's like a guitar. One takes this string, pull it, and since it's under the stress, then applying piezo element, one excites the eigenmode of the string, which makes this resonator to move. And you see that this is a micron, so this is 2 micron, and this is a 10 micron. You see that on the chip there are, well, for this particular experiment, this is a field of my expertise, there are 44 mechanical resonators, and this is really something which appeared only for a few last years, and this is one of interesting, very modern branches of nanophysics. There will be a conference in ICPP at the beginning of September about nano and opto-electromechanical, nano-electromechanical and nano-optomechanical devices, let me say it that way. And of course, working on nano-electromechanical devices and not working on optomechanical devices, I should mention that these optomechanical devices like cantilevers, which the mirror attached on membranes, can, for example, be used for detection of gravitational wave. There is at least hope how to make devices extremely sensitive in order to check one of the basic conditions of attempts to construct a general gravity unification system. So you see the frontiers of modern experimental physics, and those things which sounded like science fiction even 10 years ago now come to reality. So I'm not showing you computer simulation. This is electronic microscope pictures. So these are real pictures of real devices which are workable and which exist in us.
Excuse me.
Sorry, question?
These devices are now produced in the industry or are still under study in the lab?
It's a good question. Well, in Munich, and this picture is taken from my friends and colleagues in Ludwig-Maximilian University in Munich. They have a company which is affiliated with the university, which produces some nano-device which includes mechanical component. So this particular one is just experimental device in order to study behavior of these resonators, low frequency resonators. But you know, nowadays the way between experimental studies and industry is very short. Tomorrow, the day after tomorrow, we'll discuss quasi one-dimensional and quasi two-dimensional systems like carbon nanotubes and graphene, and you will see that there are several projects, industrial projects, both for nanotubes and graphene, which probably come to industry or will produce some industrial devices in this year. So there is at least hope with graphene devices that it will be the case this year. I think there are some application of quantum dot devices, industrial application these days too, especially in cell phones and more questions. Another way to think about miniaturization and objects to be used for new electronics, and I'm talking about future electronics, something which may not necessarily happen tomorrow, but one of the promising direction to happen in next decade is molecular electronics. So molecular devices also possess high controllability. So you see, for example, that this is a cell sand. So there is a cerium atom surrounded by hydrocarbon rings, and being put between source and drain on that sort, it can work as a molecular transistor, and then again it has some mechanical ingredients, since molecule, such kind of molecule containing a transition metal inside. There are some vibration modes which can be induced by transport. For example, if you put source and drain, and if the single electron transport occurs such a way that extra electron hops to this molecule, the molecule is deformed. The deformation of molecules means excitation of some phonons or optical phonons in the system, which is now vibrant. So mechanical component or interaction between electron and phonon degrees of freedom is indeed important part of the theory of this system. And last but not least, is these transition metals used for this kind of chemistry is a source of spin, and therefore this kind of molecular electronic device can be used as spintronics device too. Those of you who time to time look into archive, and I strongly recommend you to look into archive just for understanding what are directions of physics, may realize that for last year there is yet another field of electronics which was invented, which is now called topotronics. This is topological electronics, which is based on some interesting topological properties of systems, non-trivial topology system. So you see, in addition to standard, so to say, electronics, which becomes not really standard on a nanoscale, there are another branches of electronics, mostly dealing with spintronics, dealing with topology, topotronics, and Who knows? And maybe all this direction will be a route to nowhere, although doubt. Maybe next day, next week, next month, next year, something revolutionary new come, and we will be all facing a revolution in the field. But maybe one of these directions is really promising and will be the mainstream of electronics of next or this edition. So, starting to speak about molecular electronics, this is another example. This is a bucketball. So you see the fullerene C60 or C70. There are several of them, which just illustrates the fact that being put on a gold surface, gold substrate and subject to nanotip, if there is STM scanner tunnel microscope affecting the system from this side, it actually again ignites some mechanical component because the fullerene can oscillate, being charged and discharged and recharged, and it also changes shape. And modern electronics, modern chemistry allows to put something inside of fullerene. This is what I'm going to show you. But again and again, being put under the source and drain, where the source could be the nanotip and drain can be the gold substrate. It's again a transistor. The name for this transistor is molecular transistor, and this is the same way good single electron transistor to deal with this electronics. As I said, one can put some molecular complexes inside. This is scandium nitride complex put inside of the fullerene. By the way, the size of this fullerene is 5 to 7 angstrom, depending on mechanical formula of it. So you can imagine the scale of electronics and chemistry one operates now in order to produce the building blocks for a computer. So these are two lanthanum atoms sitting inside C60 or C70, so they can really again gives you an idea how big lanthanum atom is if it is sitting inside of 7 angstrom fullerene. Another object which I will be talking tomorrow, not tomorrow, the day after tomorrow, is this carbon nanotube device. So I'm not going to spend much time here. I only want to say that if one takes the single layer of graphite, which is now they call graphene, and wrap it in some particular direction, one has a tube. And this is quasi one-dimensional object because size of this tube could be much longer compared to diameter. Just to give you impression, the typical diameter of single-wall carbon nanotubes is about 20 angstroms, while the length of this nanotube can be of a few micron size easily. So you see the contrast and aspect ratio between diameter and length. However, the short segment of the nanotubes put between source and drain can also play a role. Short means 100 nanometers. Nanotubes can also be used as single electron transistor. So this carbon-based electronics, which is implemented in the way of graphite, graphene, nanotubes, could also be one more promising direction of future electronics. We discuss the physics of quasi one-dimensional object next time, and now I want to combine this object. This is not lithography, this is of course computer simulation, which shows the single wall carbon nanotube with the fullerenes inside and with the transition metal at inside, which is gadolinium in this case. So you see one can produce kind of nanocrystals, well-packed nanocrystals inside of nanotube. This is why it is called ether. By the way, and CMT is a single, is carbon nanotube, a single wall carbon nanotube. Of course, in what I'm